Hello, my name is Benedict Bunz, and I'm a PhD student at Stanford University. I'll be telling you about FlyClients, which are super light clients for cryptocurrencies. This is joint work with Luciana Kiffer, who's a joint first author, Loya Lu, and Mari Zamani. Let's begin by recalling the standard blockchain format. So as the name suggests, a blockchain is a hash chain of blocks where every block contains a hash pointer to the previous block. This is just simply the block of the previous block header, where the block header also has the root of a Merkle tree, and the leaves of the Merkle trees are the transactions themselves. So this is what we refer to as the Merkle, as the block header, versus this lower box here is the data of the block, or the block's transactions. And in order to verify that a block is valid, or an entire blockchain is valid, I need to check a couple of things. I need to, of course, check that the transactions are valid, that they're correctly assembled in the Merkle tree. And then additionally, I need to check that the block header is valid. So how do I do that? Well, there's two things to verify. The one thing to verify is that the block header has a correct pointer to the previous block. And then additionally, I'll have to check that the block starts, the hash of the block itself is really, really small. So it starts with, say, 70 zeros in Bitcoin in binary format. And how can this be the case? Well, there's this additional nonce field here, which the miners insert, and they will try different nonces in order to find one that makes the block have a small hash. And this is what we call mining. And then this final result is the so-called proof of work, because it proves that a lot of work went into creating this block. How much work? Well, to create a block that starts with 70 zeros, I need to do an expectation 2 to the 70 amount of work in order just to find a single one. And the other property is that I can easily verify that a block is valid. Why is that? Well, because checking that the proof of work is valid is just a single hash in a single comparison. So what does this give us? It allows Alice to succeed in this following scenario, where she's presented with two different blockchains and they both claim to be correct. And let's say both of them are internally consistent. So they only have valid transactions and they only have valid proof of work. Well, how can Alice decide which one is the correct blockchain? She just simply uses the so-called longest chain rule, where she will take the chain that is longer, that has more work put into it and was an expectation harder to produce. And what is the intuition behind this? The intuition is that if the majority of miners is honest, the majority of computation power is honest, well, then they will work on the longer chain, because these are part of the rules of proof of work blockchains. And this chain will be longer than anything any adversary could come up with. And this is the so-called longest chain rule. And people have proven that this, in fact, leads to a secure blockchain. So the problem that we're trying to address today with FlyClient is that the size of these blockchains keeps growing and growing. So for example, here, this is, I think the Bitcoin blockchain is over 150 gigabytes. And for Ethereum, we're already at I think, a terabyte. And there's no way that a mobile client can possibly download, store, or verify this amount of data. And Satoshi actually foresaw this problem and created something called a simple payment verifying client, or a light client. And the idea was that this light client, this SPV client, only stores the block headers. Because using these block headers, the light client can still verify that the that the proof of work is correct. It can still verify that all of these block headers are internally consistent. And you can use this to still use the longest chain rule in deciding which blockchain to follow. The problem is, of course, that the client doesn't know that all of the transaction is valid, because it doesn't even download all of the transactions. But that turns out to be okay, because if by assumption, in fact, the longest chain is produced honestly, and this is the assumption that the entire security of the blockchain relies on, well, then we can simply, then it's okay, because the honest chain would never create an invalid transaction, because honest nodes would never extend a chain or that has an invalid transaction in it. So by assumption, I can simply, this implies that the longest chain, the one with the most work, will only contain valid transactions. Additionally, this SPV client can verify that a transaction was included in a particular block, and it does that using a simple Merkle proof, which some friendly prover, some friendly so-called full node can provide. And the SPV clients, they have many applications and many good properties. For example, the main one that it doesn't grow with the number of transactions. But they also have some downsides, and one of the key ones that we're going to focus on today is that the size of this SPV client still grows linearly with the number of blocks. And in Bitcoin, this is 40 megabytes, but in Ethereum, this is already 2.2 gigabytes. So already probably too large for a mobile client. And one of the problems in Ethereum is that the block headers themselves are larger, so they're half a kilobyte. And additionally, there's a new Ethereum block every 6 seconds. So this creates a larger SPV client because there's more blocks added, or they're added at a more rapid rate. And especially this is a problem for, say, multi-chain clients that want to download and store multiple blockchains and use this for atomic swap applications. And there is prior work that attempts to address this called NIPOPOW, non-interactive proof of work, and this is a very beautiful work. But it has a few limitations that we're addressing in FlyClient. One of them is that it cannot deal with variable difficulty. So it cannot deal with the fact that the difficulty might rise or might be a rise or change, fall. And additionally, the NIPOPOW proofs, they're succinct, they're sublinear in the number of blocks, but only if there's no adversary. What this means is that an adversary could attack the NIPOPOW client to make the efficiency go down. Maybe this is only a theoretical concern, but still, something to note. So what does FlyClient look like? What is the approach that we use? Well, the key approach is that a blockchain looks kind of like a linked list, right? There's the blocks are connected, through pointers. And if you recall maybe from your computer science class, what should you do when a list isn't good enough anymore? Well, what you should do is you should use a tree. And this is exactly what we want to do in FlyClient, where every block now contains the root of a tree, and the tree, so this is a Merkle tree or Merkle mountain range, and the tree links to all of the previous blocks using a tree structure. And then the FlyClient will only store this final block header. But this tree structure allows you to reference very old blocks. So say this block is 1 million blocks in the past, very efficiently, using only, say, 20 hashes to connect these two blocks to each other. Because obviously the depth of a tree is logarithmic in the number of elements. And using this, I can now verify that some old block head is part of the correct chain using exactly this, only these logarithmic number of hashes. And then if I want to verify that some transaction was part of this old block, then I can use, the same Merkle proof that I had before to show that this transaction is actually part of the block header. So, and this is now only logarithmic in the number of transactions. So verifying an old transaction is now a log of the number of transactions per block, plus logarithmic of the number of total blocks. But the problem that presents itself is that how can a FlyClient do this check where it is can check which of the two chains that it sees is valid, right? It cannot go through all of the block headers anymore because it doesn't even want to download these block headers. So how can it correctly synchronize with the chain and be sure that it downloaded the correct chain? Well, what we're going to do is we're going to leverage a slightly stronger assumption than before, where we say that we assume that the adversary has only a fraction, a C fraction of the mining power of the honest chain, and that this fraction is known. So the protocol is parameterized by the set fraction. So as an example, let C be 1/3. So the adversary only has 1/3 of the mining power of the honest chain. And it turns out that even if you set C to be something like 90%, the protocol is still quite efficient. So you can really play with this parameter a little bit. So what is the strawman proposal? Well, Alice is just going to use her block headers in the Merkle tree to query a number of random blocks. And if you look at these chains, we have the honest chain here, which only creates valid blocks, right? This is why it looks like a sort of a solid line. But the malicious chain, either it's significantly shorter than the honest chain, in which case, it's very easy for Alice to decide which one is the honest chain, or it claims to have the same length as the honest chain. But in that case, there must be a lot of blocks in here which are in fact invalid. So in fact, only a third of the blocks in expectation can have a valid proof of work in here. And pictorially, this kind of means that the malicious chain has a lot of holes in it. So what we will do is we will simply query the honest chain at all of these points and get a block in return and verify that this block has valid proof of work. But if we do the same thing for the proof of work, we might hit a couple of blocks, that are in fact valid. But at some point, we will hit a block that is in fact invalid. We will hit one of the holes. And it turns out that, if in fact the parameter is 1/3, then we only need to query 81 blocks to get an overwhelming probability of catching an adversary. The cheating probability is 2 to the minus 128, so cryptographically small. So the problem with this strawman, why aren't we done, is that the adversary doesn't necessarily have to create the whole chain. It can decide to fork at some point from the adversary and simply from the honest chain and simply create a fork that starts after this point. And now if we queried over the whole chain, then we wouldn't be guaranteed to catch the adversaries because most of our queries would fall into this long, solid line that is part of the same chain. But it turns out that if we just knew the fork points, then this would suffice. Why is that? Well, we could simply use the same strawman proposal that we had before to sample blocks after this fork point. And again, we only need a constant number of queries after this fork point to catch the adversary. So we want to find the fork point. So how can we do that? The core idea here of now this is not a strawman anymore, but our protocol is that it suffices to not know the exact fork point, but a simple bound on the fork point. So what we will do is we'll sample enough blocks to know that if the adversary, if the chain is adversarial, well, then he must have forked after the, say, halfway point. So we sample enough blocks such that at least 2/3 of the blocks were created honestly, otherwise we would have caught the adversary. So what does this mean? It implies that, okay, he must have forked after the halfway point. And then we can continue this protocol recursively, and after a logarithmic number of rounds, we will simply check the final L blocks manually to prevent short forks. So this is the final check. And if we look at this protocol, we can look at the probability that a block is queried. So 0.0 here refers to the early blocks, so the genesis block, and 1.0 is the head of the chain. And we can see that the later in the chain, the higher the probability is that a block is in fact queried. And the final blocks are always queried. This is the final L blocks here. So this protocol kind of looks a little bit, this distribution looks a little bit rough. It looks a little bit like a step function. So what we did is we used some analysis to find actually the optimal function that gives us the lowest number of queries we could possibly have. So this gives us a much smoother querying distribution, and then we sample from this querying distribution to get whatever blocks we want to query. Additionally, we are able to deal with the variable difficulty. I'll quickly sketch this only within the following way. Well, the Merkle tree that connects all of the blocks will now have weights in it. So it will say, for example, that the total weight of the blockchain is 70, and that in the first half of the chain there's 36 weight, and then the right half there's 34. So always the two leaves or the two children need to add up to the parent node. And we can use this sort of weighted Merkle tree to now, in our querying distribution, to get a protocol for a variable difficulty client. Right here, you can see that this block has difficulty 5 versus this block has difficulty 13. So how do we do that? Well, we simply now want to, if we now get a sample from our distribution and it says, say, 0.4, well, then this doesn't mean we should check, the block at sort of level 0.4. So if we have 100 blocks, we shouldn't check the 40th block, but it means that we should check the block where 40% of the weight happened before this block. And so in this example, this would be 40% of 70 is 28. So we can simply very easily go down the tree and verify that this should be the third block. And additionally, we need to verify that the difficulty transitions are correct, but you can read about that in the paper. We also make the protocol non-interactive using basically the Fiat-Shamir heuristic. So the randomness is now derived from a hash function and the chain head itself. And looking at the evaluation, we get the following parameters. So for these different colors correspond to different levels of C, so to different assumptions for how powerful the adversary is. But we see that even if we take the most conservative assumptions, we get a proof size of about 3.5 megabytes. And this compares to, this is for Ethereum numbers, this compares to a a standard SPV client, which has to download 2.2 gigabytes. So even in the most conservative case, we get a factor of 1,000 improvement. And of course, the longer the chain is, the larger the improvement we'll get, because the proof size only grows logarithmically. So the FlyClient has actually seen some attention in practice and been deployed in practice in several blockchains. And one of the nice things that, again, you can read about in the paper is that you don't need to have a hard fork. You don't need to have a complex fork to replace, whatever data structure you had before. It simply suffices to use a so-called velvet fork and put the MMR in the transaction which is included to the block. And additionally, you could also use a smart contract which simply stores the MMR. So it's very easy to deploy. Thank you very much. You can find the paper online, and I'm excited to hear your questions.